Professor Bridges has posted them. I'm not Canadian. I'm Texan. Right? They'll be posted when they're finished grading, when they have been graded. So today's module is on, basically as it says up top, limits, continuity, and L'Hopital's rule. So lots of L'Hopital's rule, to be honest. It's the same apartment. I haven't moved. So if you go, okay, I'll show you how to do that. Can I show you how to do that? Let's see. Yes. Excuse the matrix. So you go to, yeah, Taves was moving, not I. You go to, yeah, exactly right. You go to this page, which is where you've been accessing these lectures or these rooms, and you go to this like top 3 lines thing, recordings. And then here they all are. So this was our last class, Sean Rogers lecture, recording number 7. All right, so let's go back to the review. All right, so we're looking at limits. So this first problem, kind of similar to the last review, is just a big smorgasbord of a bunch of limits. We'll do a couple together, and then I'll break you into groups and have you do the rest, and then we'll come back together on those. All right? Okay, so the first one is the limit as x approaches 1 of the square root of 5x plus 6. All right, so how do you think we do this? Very good, Matt. Just plug it in. There's no issue here, right? I'm not like dividing by 0, or I'm not taking, I'm not dividing by 0, so there's not really much of a problem here. Yeah, exactly. So you should always start by plugging it in, really. That should be your first instinct, is to think, well, what happens if I sort of pretend I'm 5 years old and I just plug the number in? Well, then I get square root 5 times 1 plus 6, which is just square root 11, right? Like, there's no issue. I do chuckle, indeed. Keeping our spirits high in solidarity. Shoot. If I was paid. That's right. All right, so let's look at the next one. All right, so now we're taking a limit, the limit as x goes to infinity of this rational function. All right, so as x goes to infinity, both of these polynomials will go off to infinity. Any polynomial will. All right. Yeah, we know about the group me too, so don't try to be too slick with that. All right, please hinder the reference to federally illicit substances in the chat. All right, so as x goes to infinity, both of these terms will go to infinity. So we've seen a few different ways to do this now. One way is like the pre-cal way, where you're just looking at the degrees. We also divided everything by the highest power in the denominator, so that's sort of the most complicated way. Another way to do, what's like another way of solving this limit if I get infinity over infinity? Exactly. L'Hopital's rule. All right, so by L'Hopital's rule, I just take the derivative of the top and bottom. All right. So what's the derivative of 2x squared minus 3x? Minus 5 as well. Good. 4x minus 3. Extra credit for Caleb. Who's first? All right. What's the derivative of 3x squared plus 7? Oh, Sam's jumping the gun there. All right. 6x. True. Congrats. All right. So now what happens if I let x go to infinity? What does it look like? Still looks like infinity over infinity, right? But that's fine. Got to do it again. That's right. Here we go again. All right. So the derivative of 4x minus 3, though, is, of course, just 4. The derivative of 6x is just 6. And this then just is 2/3 simplified. Indeed. Okay. I mean, I think simplifying from 4/6 to 2/3 is good. 2 plus 2, that's 4. Can y'all hear these people talking outside my room? Sounds of the city. My apartment engineer. I'm not moving. Okay, let's move on. But let's move on. Ooh. All right. So the next one, we have another limit of a rational function going off to infinity. So this will still look like infinity over infinity, right? Okay. So if you take, we can do the same thing basically. We'll do like a few successive L'Hopital rule applications. So if I take the derivative of x squared minus 5x minus 5, I'll get 2x minus 5. If I didn't write the limit. Minus points. If I take the derivative of 7x cubed plus x squared minus 7x plus 9, I'll get 21x squared plus 2x minus 7. Good. And I'll still get 0 over 0. Or sorry, infinity over infinity. All right, so you just do it again. Now we get the derivative of the top will just be 2. The derivative of the bottom will be 42x plus 2. Okay, so now what is the limit if I let x go to infinity? It is 0, right? Because I get 2 over infinity, right, Jared? Which we sort of think of as being 0, basically. The numerator remains a fixed value, and the denominator gets arbitrarily large. As long as it's a degree 1 at least, yeah. Or I mean, it could be like negative infinity. One of the infinities could be negative, or both could be negative. Well, to start out with, if it's any, like it doesn't matter what the degree, as long as the degrees are at least 1 to start out with, you'll get some kind of infinity over infinity. If I take x divided by x to the 10th plus 5 and let x go to infinity, that will still be infinity over infinity. Second derivative, L'Hopital's rule. Because the first derivative is the sort of like linear approximation. So if you zoom in, at least in the 0 over 0 case, that's what it looks like. Yeah, you would still, yeah, and the second derivative is just the derivative of the first. So in this case, we did take two derivatives, right? So yeah, if you have negative infinity over infinity, you'll still use L'Hopital's rule. We will not have a final sum. All the midterms and tests are replaced by these modules. Okay, so let's look at the next one now. If I let x go to 0, that's right, don't forget. All right, so if I let x go to 0, then I get something that looks like e to the 0th power minus 1 plus 2 times 0 divided by 0 squared. All right, so what is e to the 0? Just 1, right? So the 1, I get 1 minus 1, which cancels out, and then every other term is 0. So this looks like 0 over 0. Okay, so what rule will we use? Children. Little hoppy. All right, good. So we get, so what's the derivative of e to the negative 2x? Good, negative 2e to the negative 2x, right? The derivative of e to some function will be e to that same function times the derivative. So the derivative of negative 2x is negative 2, and then we still have e to the negative 2x. All right, for the rest of the numerator, the derivative of negative 1 is 0, the derivative of 2x will be plus 2, and the derivative, that's true. Right, the derivative exactly of x squared is 2x. Thank you. All right, so now what happens when we plug in 0? Good, we still get 0 over 0, because you get the numerator becomes negative 2 plus 2, and the denominator is 2 times 0. So you still get 0 over 0. Right? So we do L'Hopital's rule one more time. Okay, now what does the derivative of the numerator look like? Good, right? You just multiply by negative 2 again, basically, for the exponential term. So you get 4e to the negative 2x, and the derivative of 2x. Got it. Third time's a charm. All right, so now what happens when I plug in 0? Good, you get 4 over 2, or just 2. Look at y'all, superstars. Preach. All right. As to the extra credit that I claimed earlier, officially there's no extra credit. Unofficially, there's also no extra credit. All right, so now I want y'all to work on these last 4, and I'm going to put y'all into groups. Yeah, you can get a virtual pat on the back. Yes, that's today. Yeah, that's what we're reviewing for. All right, so I want y'all to work on these next four. Well, as x goes to infinity, root x would also go to infinity. So it actually looks like infinity over infinity. Some feedback. Is that for me? Yes, it was for me. Hottest new mix. Okay, so looking at this first one, what does it look like if I let x go to infinity? Sorry, yeah. Good. Still looks like infinity over infinity. All right, this one is a bit involved. Let's brighten our colors up a bit so as to brighten our mood. So we use L'Hopital's rule. Okay, so the derivative of ln of x cubed, you're going to have to use the chain rule here. All right, so you'll bring the 3 down. So the outermost function is the power rule. All right, so you'll bring the 3 down, still have ln of x in there, squared, times the derivative of ln of x, which is what? Good, 1 over x. Okay, and what is the derivative of square root x? Good, 1 over 2 root x. Okay, so remember that dividing by a fraction is the same thing as multiplying by its reciprocal. All right, so this is the same thing. I'm not writing the limit, I'm just like altering the expression as 3 ln of x squared times 1 over x times the reciprocal of 1 over 2 root x, which is just 2 root x. Okay, so this ends up being the same thing as the limit as x goes to infinity. So let's see, what do we end up with? So 3 times 2 is 6 ln of x squared divided by root x. Okay, because root x over x is equal to 1 over root x. No print. The 6 comes from the 3 times the 2, looking at like this term here. And then the root x over x gives me the root x in the denominator. All right, so this is a bit, what does it say inside parentheses? ln of x. Yeah. All right, so then we do the same thing. We Okay, and we're back. All right, so we get infinity over infinity again, basically. All right, so you take the derivative again using L'Hopital's rule. All right, so the derivative of the top, you'll use the chain rule to 12 ln of x times the derivative of ln of x, which you said was 1 over x. And on the bottom, we have like root x again, so we get the same derivative as before, 1 over 2 root x. Okay, so this ends up being the limit as x goes to infinity. And you would do the same thing. You're dividing by a fraction, so you multiply by a reciprocal. So we get something similar. We get 12, or no, we get 24 ln of x divided by root x. Very good. All right, so we get infinity over infinity again, and we use L'Hopital's rule again. So then we would get just 24 times 1 over x, so 24 over x, divided by 1 over 2 root x. And this is 48 over root x. Yes, now you get 0. Because he's quarantined. All right, so all that, so you have to use L'Hopital's rule several times, basically. But don't get like too discouraged if you end up getting infinity over infinity and stuff like that again. All right, so now let's look at the next one. So I would say that with these trig functions, a lot of times it's easiest if you just like write everything in terms of sine and cosine. So cosecant is 1 over sine, right? Okay, so if cosecant is 1 over sine, this just becomes sine of 7x divided by sine of 6x. Can you hear me? I take no responsibility for whatever Mayor Lightfoot said in my absence. Okay, so here we are. Okay, everything's running smooth. All right, so we want to basically rewrite trig functions here in terms of just sine and cosine. So cosecant is 1 over sine. So this looks like sine of 7x over sine of 6x. All right, so what is sine of 0? Good, 0. So this looks like 0 over 0. All right, so what is the derivative of sine of 7x? Don't forget the chain rule. Good, 7 cosine of 7x. So then the derivative of sine of 6x is 6 cosine of 6x. Yep, so cosine of 0 is just 1. So now if I plug in 0, you really just get 7 over 6. Okay. All right. So I'm going to skip G for now since I got sort of sidetracked there because I want to get through some of the rest of these problems. But let's look at H real quick. All right. So here, if I plug in 1, this looks like, so sine of pi is 0. So if I plug in 1 to pi x, I get pi. So this looks like 0 to the 0th power, which is an indeterminate form. Yeah, exactly. So we use a logarithm. So we're going to set L equal to the limit as x approaches 1. Actually, let me just... Okay, and we're going to take the natural log of both sides. When we take the natural log, you can, yeah, basically, you need to get into 0. Well, 0 over 0 or infinity over infinity, yeah. So use the natural log to bring the sign down. I don't know why it's like erasing and then showing back up. But anyways, so now if I plug in 1, this looks like 0 times negative infinity. All right, the trick here is to move one of the terms into the denominator. So I'm not doing any, like, I'm not changing anything, I'm just rewriting it. I'm moving the sign into the denominator so that I get like 1 over sign, which I could also write as cosecant. So I'm just rewriting this as ln x minus 1 over cosecant pi x. Now this looks like negative infinity over infinity. Okay, and now I can apply L'Hopital's rule. So let's see. The derivative of ln of x minus 1 is 1 over x minus 1. the derivative of cosecant of pi x is negative pi cosecant x, pi x, cotangent pi x. Well, 1 over 0 does go to infinity. Any like finite, if you think of a finite value divided by like 0 or some sequence approaching 0, you think of that as either a positive or negative infinity. Yeah, it's like an asymptote. Okay, so now if I let x go to 1, or you know what I can do is we can actually rewrite this in terms of sine and cosine again. And this will be, let's see, what do we get? Oh, the pi should be in the bottom. Yeah. Okay, so this might look like a big step from one to another, but I'm just writing the cosecant and the cotangent in terms of sine and cosine, and then like just using the rules for fractions, right? Okay, but now this will be this will go to 0 over 0, and we use L'Hopital's rule again. Okay, so then we'll get, let's see, negative 2. I wonder if there's room here. Okay, and then on the denominator, you use the product rule. So let's see. Okay, and now if you plug in 0, I know this is a bit like much here with all these terms, but if you plug in 0, you get 0 over pi, which is just 0. Okay, I'll write this out a little cleaner in the solutions that I post, but we gotta move on to this stuff. All right, so what conditions must a function satisfy in order for it to be continuous at a? Yeah, we are done. So we got 0 over pi, so 0 over any like finite value is just 0. Oh, you're right. Thank you, Howard. So we got 0, so this is a common mistake that people made on the homework and now I'm making. So, right, we started this off by setting L equal to this limit and taking the natural log. All right, so what we actually have is that the natural log of L is 0, which means that L equals e to the 0th power, or just 1. Yeah, I'll put these up later. Like a bit after class ends. Okay, so what does a function need to be continuous at a point A? So there's three conditions. The function must actually take a value at A. The limit must exist as well. And they have to be the same. Okay, so now one like continuity type question is that you'll look at is one of these like piecewise functions with some parameters. And we want to like choose parameters for A and B that would make this function continuous at 1. So we're going to take the left and right hand limits, and like one condition is that the limit must exist. So the left and right hand limit have to exist, for example. All right, and it also has to equal the value of the function. Okay, so we're going to look at three things here basically: the limit from the left, the limit from the right, and the value of the function. So the limit from the left so if I'm approaching x from the left, that means that I'm like living in this part of the domain, the x less than 1 part, right? So I use that function. So what we want to see is something like this, like you're writing the limit as x approaches 1 from the left of f of x. This is equal to the limit as x approaches 1 from the left. And now you replace f with the actual equation that you're using here. So if I'm approaching 1 from the left, I use 5x minus 2. All right, and there's no issue here now with plugging the limit in. I just sort of plug 1 in. So I get 5 minus 2, or 3. All right, the limit from the right so if I'm approaching 1 from the right, then I'm sort of living in this part of the domain, all right, where x is greater than 1. So this is the same thing as the limit as x approaches 1 from the right of ax squared plus bx. All right, so a and b are just some numbers, all right, but x is what depends on the limit here. So I can just plug in 1, and I get a plus b. Okay, and then finally, I also need to know what is the actual value of the function at 1. So if I just plug 1 into the function, what do I get? Good, a, exactly. All right, that comes from this middle part, where it says when x is 1, f of x is a. All right, so all three of these quantities really need to be equal to each other. All right, in order for the limit to exist, the left and right hand limits need to agree with each other. And then all of like both of those together need to agree with the actual value of the function. Well, all three of these things need to be equal, basically. So if 3 is, like 3 has to equal a, basically. The Riemann stuff will not be on this module. Nope. Yes, and then b has to be 0. That's right, because 3 also has to equal a plus b, but we just saw that 3 equals a, or that a equals 3 is better. So then we get 3 equals 3 plus b, which tells me that b equals 0. No. This is covering limits and continuity and L'Hopital's rule. Okay, so I know it's 350, but there's just one last problem, which we can honestly do pretty quickly here. So we're given this graph on the right, and there's three particular values we're looking at: -1. Stop it. I don't care. 2 and 3. All right, so these are values we're substituting in for A: -1, 2, and 3. All right, so we're doing that in a chart or a table here. All right, so this first part here, if I take the limit as x approaches -1 from the left, what will I get? Yep, 3. All right, so let's do it one value at a time, so -1. So we'll move down the first column. All right, how about if I approach -1 from the right? Good, 1, right? You're just following along the chart, right? And then, does the limit itself exist? Good. Because the two values above it are not equal. All right, and then finally, what is the value of f at -1? Good, 1. Here, you're just looking at the filled-in dot. All right, now let's move on to 2. If I take the limit as x approaches 2 from the left, oh, sorry, not -1. Yeah, thank you. If I take the limit as x approaches 2 from the left, what do I get? So yeah, if I approach 2 from the left, my y coordinates are going to 4. Okay, and then as I approach 2 from the right, good. And then does the limit exist? And if so, what is it? Yes, 4. 4, yes. All right, and then what's the value of the function at 2? Good. All right, last one. If I approach 3 from the left, what do I get? 3. Look at you, experts. If I approach 3 from the right, good. 5. What's the next thing I'm going to say? No. I'll assume they're correct, Sophia. All right, and then finally, what is the value of the function at 3? Good, 5. Okay, perfecto. All right, awesome. Okay, so thanks for stopping by. Good luck on your module. It'll be posted at 5. I'll post solutions to this. I'll clean them up a little bit and post solutions. It'll probably take me like 15 minutes or so. Yeah, y'all too. All right, thank you, Mayor. There's 5 in total, so this is the second one. Yep. Yeah, Mohammed. It's true, they are worth a lot. But you do have a lot of time to do them. I know it's like over the weekend, which is kind of weird. But yeah, I mean, and you have it's open, but it's open note too. So I would like to look at like past homeworks and stuff that are relevant to the material, and look at the solutions that are posted particularly. A lot of times the students are like they kind of have the right idea for how to solve them, but they're not so great at justifying their answers, which is what part of what the module is doing. So look at like those posted solutions. Yep. The grading for the first module is almost finished, so they should be posted soon. I can't say. I'm not. There's someone still needs, like, the grading is divided up by a bunch of people, and someone still needs to finish their grading basically. So whenever they finish it, it should be, I assume, over the weekend. Yep. Yeah, you have two attempts. On the quiz last week. You mean the, like, my math lab quiz? You should be able to, like, check what you put. Like, you should be able to, like, log back into the assignment and see what answer you put. You can't log back in. Can you look back at your homeworks? Like, what answer you put? Can't you?